Here's an example, and it says, a fair six-sided die is tossed once. Determine the probabilities of the following events. The first event is obtaining an even number. The next one is obtaining an odd number, and the last one is obtaining a 3 or a 6. So let's start with case A. I'm going to define the event obtaining an even number with the symbol A. So A just represents the event obtaining an even number. And a good place to start is to just represent the sample space of activity. We're tossing a die and there are 6 possible outcomes. 1, 2, 3, 4, 5, and 6. And each of these outcomes represents a possible number on a side of the die. Now, the probability of obtaining an even number is going to be equal to the number of desired outcomes, which is the same thing as the number of ways of obtaining an even number, divided by the total number of possibilities, the total number of outcomes. And how many ways can you get an even number? Well, how many even numbers are there in the sample space? Here's one, here's another one, and here's another one. So there are 3 possible ways of obtaining an even number out of 6 possible outcomes. So the probability of obtaining an even number is 3 over 6, which is equal to 1 over 2, which is the same thing as 0.5. In case B, we need to determine the probability of obtaining an odd number. So I'm going to define the event obtaining an odd number as B. So I'm going to call this event B. What's the probability of event B? The probability of event B is equal to the number of ways an odd number can be obtained, or the number of desired outcomes, which is the number of outcomes that result in one choosing an odd number, divided by the total number of outcomes. And just have a look at the sample space. How many odd numbers are there? Here's one, here's another, and here's another. So there are 3 possible ways of getting an odd number after the die toss. So 3 divided by the total number of outcomes, which is 6. So the probability of obtaining an odd number is equal to 1 over 2. So this B here, I'm just using it to represent the event obtaining an odd number. And finally, in case C, we need to determine the probability of obtaining a 3 or a 6. And I'm going to call this event, I'm just going to call it C, just a safe space. So we need to find the probability of C. And that's going to be equal to the number of ways one can get a 3 or a 6 divided by the total number of outcomes, or the total number of possibilities, whichever way you want to think about it. Now, in how many ways can you get a 3 or a 6? Or how many desired outcomes exist that will satisfy this event? If you look at the sample space, there are only 2. Here's one, getting a 3. Here's another, getting a 6. So there are 2 possible outcomes for the desired event, divided by the total number of outcomes, which is 6. So the probability of obtaining a 3 or a 6, which I'm representing with C, is equal to 1 over 3. And that's it. Here's another example, and it says, a bag of sweets contains 20 sweets in total. 2 sweets are selected successively. After each selection, the chosen sweet is replaced. Remember this. Here is a summary of the bag's contents. So we have a bag of sweets, and it has sweets of different flavors. It has 20 sweets in total. Of the 20 sweets, 6 are lemon flavored, 4 are mint flavored, 9 are strawberry flavored, and 1 is orange flavored. The question now says, determine the probabilities of the following events. A. Choosing 2 lemon flavored sweets. B. Choosing 2 strawberry flavored sweets. And C. Choosing a mint flavored sweet followed by a strawberry flavored sweet. So that's the question. A key part of this question is this word replaced. And here is its significance. Remember, 2 sweets are being selected. So imagine I choose a lemon sweet the first time. Once I choose that lemon sweet, there'll be 5 sweets left. But if you replace the sweet, if you put the lemon sweet back, all of a sudden there are six lemon sweets before you now choose your next sweet. Similarly, if you choose a strawberry sweet the first time, there'll be 8 strawberry sweets left. But if you replace the strawberry sweet, there'll be 9 strawberry sweets just before you make your second choice. So that's very important in answering this question correctly. So for case A, choosing 2 lemon flavored sweets, so that's an event. I'm going to say let L1 represent choosing a lemon sweet in the first instance, and L2 is the event choosing a lemon sweet in the second instance. So all we need to do is find the probability of 2 events. The first event is that a lemon sweet is chosen in the first selection, and the second event is that a lemon sweet is chosen in the second selection. So we need to find the probability of these 2 events. As you know, the event L1 and the event L2 are independent events because the occurrence of one does not influence the occurrence of the other. If a lemon sweet is chosen in the first instance and then replaced, it doesn't affect the probability of choosing a lemon sweet in the second instance because we essentially have the same sample space. So the first choice doesn't affect anything because the sample space is the same. This will make sense shortly. But because event L1 and event L2 are independent events, and I'm just making it clear, event L1, this event here just represents the event of choosing a lemon sweet in the first selection. L2 is another event and it represents the event where a lemon flavored sweet is chosen in the second selection. Now, you know that when you have 2 independent events, the probability of event A and B, where events A and B are independent, is equal to the product of their probabilities. We've covered this. So the probability of event L1 and event L2 occurring is equal to the probability of event L1 times the probability of event L2, which represents the probability that a lemon sweet is chosen in the second instance. And this is equal to what? What's the probability of choosing a lemon sweet in the first instance? Well, it's equal to 6 divided by the total number of sweets, which is 20. Let me just put a total here. 6 plus 4 is 10, plus 9 plus 1, 20. So a lemon flavored sweet is chosen. That leaves 5 lemon sweets. But that sweet is also replaced. So this is what we have before the second choice. What is the probability of choosing a lemon flavored sweet in the second instance? It's equal to 6 over 20 again. This 6 represents the number of desired outcomes, the number of lemon sweets, or the number of ways in which a lemon sweet can be chosen in the second instance. This 6 also represents the number of ways in which a lemon sweet can be chosen in the first selection. 20 represents the total number of outcomes, or the total number of possibilities. Therefore, simplifying gives 36 over 400, which is equal to 9 over 100. So the probability of choosing a lemon sweet in the first selection and a lemon sweet in the second selection is equal to 9 over 100. In case B, we need to determine the probability of the event choosing 2 strawberry flavored sweets. So that's the event of choosing a strawberry sweet in the first selection and a strawberry sweet in the second selection. Now, again, if a strawberry sweet is chosen, that leaves 8 sweets. But because we're replacing sweets in this case, there'll be 9 sweets just before you're choosing the second strawberry sweet. The significance of that is the first choice does not influence the second choice because the sample space is the same in both cases. This will make sense shortly, but because the 2 events are independent, the probability of S1 and S2 is the probability of S1 times the probability of S2, where S1 represents the event of choosing a strawberry flavored sweet in the first selection, and S2 represents the event choosing a strawberry flavored sweet in the second selection. The probability of S1 is equal to what? The number of ways you can choose a strawberry sweet, which is 9, divided by the total number of outcomes, the total possibilities, total number of sweets, which is 20. Probability of choosing a strawberry sweet in the second selection. Remember, the strawberry sweet is chosen and then placed. What's the probability of choosing a strawberry sweet? It's 9 over 20 as well. Therefore, the probability of choosing 2 strawberry sweets is equal to 9 over 20 times 9 over 20. So I'm just applying this. 9, and this gives 81 divided by 400. In case C, we need to determine the probability of choosing a mint flavored sweet followed by a strawberry flavored sweet. So, probability of choosing a mint flavored sweet in the first selection and then a strawberry flavored sweet in the second selection. Again, the two events are independent, so the result is the product of the probabilities of both events. The probability of choosing a mint flavored sweet in the first selection is the number of desired outcomes for the number of mint flavored sweets divided by the total number of sweets, the total number of possible outcomes, which is 20. The probability of choosing a strawberry flavored sweet in the second selection is equal to the total number of desired outcomes, which is 9, divided by the total number of sweets, the total number of outcomes, which is 20. So, this probability of choosing a mint flavored sweet followed by a strawberry flavored sweet is equal to 4 over 20 times 9 over 20. And that's equal to 36 over 400. And this can be simplified to give 9 over 100, which is the same thing as 0.09. Here's another example. It's actually the same as the previous one. The only difference is this time there is no replacement of sweets. So it's the same table, the same questions as well. So let's answer them this time. Case A, we need to determine the probability of choosing 2 lemon flavored sweets. So choosing a lemon flavored sweet the first time and a lemon flavored sweet the second time. And that's equal to the product of the probabilities of the two events. What's the probability of choosing a lemon flavored sweet the first time? It's 6 over 20. 20 is the total number of sweets. But once you choose a lemon flavored sweet, there are now 5 lemon flavored sweets left. And the total number of sweets now, just before the second selection, is now 19 and not 20. So, what's the probability of choosing a lemon flavored sweet the second time? It's now the number of lemon flavored sweets, the number of desired outcomes, 5, divided by the total number of outcomes, which is now 19. And this can be simplified. Well, this is 30 divided by 20 times 19, which is equal to, if you simplify this, you get 3 divided by 38. You can just see that this way. That's 3 over 2 times 19 is 38. So that's 38. I'll write it again. So that's 3 divided by 38. Now in case B, we need to determine the probability of choosing 2 strawberry flavored sweets. So strawberry flavored sweet the first time, and then a strawberry flavored sweet the second time. So these are two events: choosing a strawberry flavored sweet in the first selection, and the second event is choosing a strawberry flavored sweet in the second selection. That's equal to the product of the probabilities. Now, what is the probability of choosing a strawberry sweet during the first selection? Well, that's the number of desired outcomes, the number of ways you can choose a strawberry sweet, which is 9, divided by the total number of outcomes, which is 20. So once a strawberry sweet has been chosen, this time we don't replace sweets, so there are 8 left. That means the total number of sweets now is not 20, but 19. Because if you add up all the sweets, you find out that there are 19. I mean, initially we had 20, and we've taken one sweet out, so there are 19 left. So now what is the probability of choosing a strawberry flavored sweet during the second selection? Well, that's the number of ways you can choose a strawberry flavored sweet divided by the total number of outcomes, which is not 20, but 19. And this can be simplified to give 18 over 95. And that's the answer. And finally, we need to determine the probability of choosing a mint flavored sweet followed by a strawberry flavored sweet. So in the first instance, choose mint. Second instance, choose strawberry. This is given by the product probabilities. What's the probability of choosing a mint flavored sweet in the first selection? That's the number of ways you can choose a mint flavored sweet, which is the same thing as the number of desired outcomes divided by the total number of sweets, or total number of outcomes in the sample space. That's 20 times the probability of choosing a strawberry flavored sweet in the second instance. So we've chosen a mint flavored sweet the first time, so we have 3 left. So now the total number of sweets is 19. How many ways can you choose a strawberry flavored sweet? 9 ways. There are 9 different sweets, 9 desired outcomes, divided by the total number of outcomes, which is total number of sweets, which is 19. And simplifying this gives 9 over 95. And that's the probability. As a fraction, 9 over 95 is the same thing as 0.0947. And this can be converted to a percentage probability by multiplying by 100. And that gives 9.47%. And all this means is that there's a 9.47% chance that one can choose, when one is choosing sweets randomly, that in the first selection, one chooses a mint flavored sweet, and the second selection, a strawberry flavored sweet is chosen. That's all it means. So anyway, you can stop here, or here, or here. They're all equivalent to each other. So here's an example question, which is related to the football transfer market, where football clubs buy footballers from other clubs. So here's the example question. It says 3 footballers have just agreed to join a football club. Before the agreement can be confirmed, the 3 footballers have to pass medical tests. The probabilities of passing the test are given below in this table, or you can look at this table here. Now, F1 is the event where footballer 1 passes his test. F2 is the event where footballer 2 passes his test, and F3 is the event where footballer 3 passes his test. And here are the corresponding probabilities. So let's just go on to the questions. We need to determine the probabilities of the following events. A, the 3 footballers pass their medical. So F1 and F2 and F3. What does this mean? This is the event where footballer 1 passes and footballer 2 passes and footballer 3 passes. So we need to find the probability of this event. And it's safe to assume that the medical test of the footballers, the results of the test are independent of each other. So these are independent events, and the probability is equal to the probability of F1 times the probability of F2 times the probability of 3. What's the probability that footballer 1 passes? It's given as 4 over 5. What's the probability that footballer 2 passes? It's given as 8 over 9. What's the probability that footballer 3 passes? It's given as 3 over 4. So the simple result is equal to whatever we get here when we multiply all these fractions out. 4 here, 1, 4 here, 1. 3 here, 1, 3 here, 3. So our result is 8 divided by 5 times 3, which is 15. So the probability that all footballers pass is equal to 8 over 15. And that is equal to 0.533, which can be converted to percentage form and I'll give 53.3%. So there's a 53.3% chance that all the footballers pass their medical tests. Finally, we need to determine the probability that none of the footballers pass their medicals. So this is what I'm going to do. I'm going to define F1 prime as the event where footballer 1 doesn't pass his test. I'm going to define the event F2 as the case where footballer 2 doesn't pass his test. And I'm going to define F3 as the event where footballer 3 doesn't pass his test. Now remember, if the probability of an event occurring, for instance, the probability of event A occurring is X, then the probability of event A not occurring is equal to 1 minus X. So I'm assuming X is a probability in the linear scale between 0 and 1. So if you apply this concept to this case, given that the probability that footballer 1 passes his medical is 4 over 5, the probability that footballer 1 does not pass the medical is equal to 1 minus, in our case, x is 4 over 5, which is equal to 1 over 5. Similarly, the probability that footballer 2 doesn't pass is equal to 1 minus the probability that footballer 2 passes, 1 minus 8 over 9, which is equal to 1 over 9. And the probability that footballer 3 doesn't pass the medical is equal to 1 minus the probability that footballer 3 passes, 1 minus 3 over 4, which is equal to 1 over 4. Therefore, the event that describes the case where none of the footballers pass is this event here. Footballer 1 doesn't pass, and footballer 2 doesn't pass, and footballer 3 doesn't pass. So what's the probability of this event? Well, it's equal to the product of the probabilities of the individual events. What's the probability that footballer 1 doesn't pass? That's 1 over 5. The probability that footballer 2 doesn't pass, 1 over 9. And the probability that footballer 3 doesn't pass is 1 over 4. And that's equal to 1 over 5 times 9 is 45, and 45 times 4 is 180. So the probability that none of them pass, instead of writing it, I'm just going to write none. Probability that none of the footballers pass is equal to 1 over 180.